My name is Alex, if I haven't met you already. I'd first like to say thank you very much to the organizers of the school. It's been super interesting coming here and learning more about neutrinos, so thank you very much. Today I'm going to be talking about some work that I started in my master's thesis, and I finished up in the first part of my PhD. I'm currently at ETH Zurich. And we looked at an early dark energy model, which has been proposed as a solution to the Hubble tension. So firstly, what is the Hubble tension? I think this plot demonstrates it quite nicely. So on the y-axis, we have the Hubble parameter, and on the x-axis, we have the sound horizon. As Olga mentioned today, this is the distance that sound waves can travel in the early universe before recombination. And the Hubble tension is then the 5 sigma discrepancy between the late time measurements of this Hubble parameter, which are shown in this orange band here. This is the most famous late time result from the Shoes collaboration. This is based on a distance ladder calibrated with Cepheids. And the discrepancy between the value you get from that and the value that you infer from a lambda CDM model, which you fit to early universe data, such as Planck CMB data, and that's shown in the ovals here. There's another contour on here. This is the model independent constraint from baryonic acoustic oscillations. And that gives you this sort of 1/x type constraint here. And the point of this plot is that if we want to solve the Hubble tension by changing our model, we not only want to raise the Hubble parameter, but we also want to lower the sound horizon. And the two things are interrelated. So if we lower the sound horizon, we'll naturally raise the Hubble parameter. So then the early dark energy model, what is this? This is exactly a mechanism to lower the sound horizon. What we do is we add an extra scalar field to the lambda CDM model, which acts like dark energy in the early universe. So you can think that in terms of this integral, we're basically raising the denominator. So more physically speaking, if you have sound waves that are propagating on an accelerated background, they won't be able to travel as far before recombination happens. So great, we have the early dark energy model. It can solve the Hubble tension. Are we done? Have we solved one of these big problems in cosmology? The answer is a little bit more complicated, as is demonstrated by these 2 papers here, which I always found quite funny. One of them basically says that early dark energy can resolve the Hubble tension and solves all of cosmology. And one published just a year later saying that early dark energy doesn't work at all and is completely rubbish. So what's going on? The problem is that when we solve the Hubble tension with early dark energy, we actually raise another problem in the model, and we worsen this S8 tension. This S8 parameter is related to the amount of clustering in the universe and the amount of dark matter in the universe. And the problem in early dark energy is that we have to increase the amount of dark matter in the universe to keep consistency with CMB data. And there's already an S8 problem in lambda CDM, which you can see from this plot here. So I should just explain, in the green band, we have a direct measurement of S8 from a weak lensing survey. This is dark energy survey year 1. And in the orange and blue bands, we have the S8 parameter you infer when fitting either a lambda CDM or an early dark energy model to CMB data. And you can see there's already a problem in lambda CDM, and we make it a little bit worse in early dark energy. And that's basically why this paper argues that early dark energy doesn't work and is ruled out by weak lensing data. Okay, so we're finally in a position to understand what I've done in this work and why at all this relates to neutrinos. I just talked about cosmology for a little bit. And it basically is all to do with this effect that Olga was mentioning today, that neutrinos can suppress the small scale structure of clustering. And I'm demonstrating this here. I have the matter power spectrum as a function of scale. And you can see that as we raise neutrino mass in a model, we reduce the amount of clustering. And the point is that in the baseline EDE model that I was showing before, they fix neutrino mass to the lowest possible allowed value from neutrino oscillation experiments. But we know that neutrinos have mass, so we don't know exactly what the mass is. And so maybe by raising the mass in this model, we can help to make the early dark energy model consistent with late time clustering results. So a quick word on our methodology. We're basically going to allow for a free neutrino mass in the early dark energy model and see if we can solve this late time clustering problem. We used 2 data sets to constrain this model. We used Planck CMB data and also BOSS galaxy clustering data. So I think we actually, Olga showed this picture before. This data set constrains both the clustering of galaxies, but also some geometrical information, which I'm going to come on to later. So does this model work when we allow for a free neutrino mass? Can we save EDE? Well, the short answer is no, unfortunately. So here I'm showing the 1D posterior distributions for two parameters in our model. The FEDE parameter, this is like the basic early dark energy parameter. This basically tells you how much early dark energy you have in your model. And the black dashed line there is the nominal amount of early dark energy we would need to completely resolve the Hubble tension. What we were hoping is that if we allow a free neutrino mass, we'd be able to shift this contour a bit to the right and allow for more early dark energy. But as you can see, it has almost no effect. In black, we have our new model with a free neutrino mass, and in red, we have the baseline model with this fixed lowest neutrino mass. And similarly, for the S8 parameter, we wanted to shift this contour to the left, i.e. reduce the amount of clustering at late times. And again, adding a free neutrino mass seems to have no effect. So this is a little bit surprising, and we really wanted to understand our results. So we also performed a more frequentist analysis. And to do this, we fixed the neutrino mass to 7 different values, and we found the best fitting cosmology using a minimization routine. And what we found was quite interesting. So the best fitting model was this baseline EDE model with the minimum allowed neutrino mass. And as you raise the neutrino mass, both the Planck dataset and the Boss galaxy clustering dataset disfavored a high neutrino mass. And we were a little bit surprised about the latter one, the Boss galaxy clustering. I mean, the whole motivation for including a high neutrino mass was that we'd be able to reduce the amount of clustering and keep consistency with late time galaxy clustering data. But the point is that the galaxy clustering data doesn't just confine the amplitude, but also some geometrical scales. So I've put a galaxy clustering power spectrum on the left here, and you can see it has these wiggles. These are the imprints of those sound waves that were set up in the early universe, but this time in the galaxy clustering distribution. And those wiggles correspond to an angular scale. And that angular scale I've plotted here for all of our different neutrino mass models. And the thing is that when you increase the neutrino mass, you also affect the background expansion rate of the universe. And this leads you to get a worse fit to this angular scale. So this is why this galaxy clustering data also didn't favor a high neutrino mass here. So to conclude, both our Bayesian and frequentist results show no benefit of freeing up the neutrino mass, which paints quite a bleak picture for the future of early dark energy. This is always, a lot of papers have been written recently, maybe some saying that early dark energy is a great model, but we haven't been able to solve the problems of this by freeing up the neutrino mass. We've confirmed that the angular position is very constraining for neutrino masses, but one caveat to all of this is that this analysis is kind of conservative in the sense that our Boss galaxy clustering data set had a lot of nuisance parameters, and a lot of the clustering information is washed out by this. So we don't really see the benefits of raising neutrino mass in this model. So it might be interesting to do some further work where you include some weak lensing data. Yeah, that's all from me. Thank you very much.
Thank you, Alexander. Do we have questions? Yeah.
Yeah, my question is, does this analysis you have made about this mass of neutrinos depend in your specific model for early dark energy? I mean, if you change the potential of your scalar field, could you get different results or different conclusions?
Yeah, that's a really good question. I think for an early dark energy model to work, every potential has to have the same sort of behavior, that you have this increase at early times, and this will always inevitably increase your clustering at late times. So I think the results of this are pretty robust against changing the scalar field, but it would be an interesting thing to check.
Okay, thank you.
Yeah.
I see Olga has also a question.
Yeah, well, actually, yeah.
So I mean, if you couple it to neutrinos, would it change?
Yeah, this would be super interesting. So I think there has been a paper that is exactly looked at this. still think you have late time clustering issues even in this model. But yeah.
Thank you. Thank you.
Yeah, question? I think then we have to move on.
Did you, when you set the neutrino mass as a free parameter, did you still have it? You still had it bounded, right, between I think it was 0.3 and 0.06, or was it completely free?
You mean here?
Yeah.
So this is a frequentist analysis, so we fix neutrino mass to several values. But when we were doing our Bayesian analysis, we just allowed it as a free parameter.
So it could be anything.
It could be anything.
Up to like TeV or whatever.
Exactly.
Okay,
There's no prior on this.
Okay. So it just doesn't work at all, no matter what the mass.
Sorry?
So you basically, no matter what the mass is, it just doesn't work.
Yeah, exactly. Basically, what we've shown is that freeing up the neutrino mass doesn't help this model very much.
Thank you.
Okay, let's thank Alexander again.